All right, so this is the second lecture on buckling instability. The first time, obviously, if you just watched it, we walked through kind of the World Trade Center and you know, some of those key aspects of the collapse. And what we're going to do now is sort of generalize some of these kind of mechanisms and things. So first thing that we're going to do is talk about what buckling is, and it is generally defined as a loss of stable equilibrium. Like that, right? And a lot of times, this sort of bowl versus dome, analogy is used. So a stable situation could look like this, right? Where I have this bowl, and in the bottom of the bowl I have a little marble, right? And if I nudge the marble to the side, right, and then I remove the force that sort of nudged it to the side, it comes back, right? It's going to settle in the bottom of the bowl, right? So in this case, that would be considered stable equilibrium, right? Now, what happens when I flip the bowl over, right? And now I have a little marble on top, and now I nudge that marble to the side a little bit, right? And this is unstable, right? Because what happens is that marble rolls off the back of the bowl and across the table and, is gone, right? So the difference generally, and a good way of remembering this, between stable and unstable equilibrium is whether or not the bowl is sort of facing up or facing down. So is it a bowl or is it a dome? That sort of thing. All right, so buckling or instability occurs when we lose stable equilibrium. So we're much more in this situation on the right than on the left. Okay, so the second thing that we have to define here is a critical buckling load. Or I guess they just call it a critical load. It's known as P critical, right? And that is the load at which buckling occurs. Okay, so if I load something up to P critical, it's at that point where it's going to become unstable. Right? All right, so then the caveat is that everything that we're going to do here is for ideal slender columns. All right. And there's a number of key sort of assumptions to this, but let me just sort of draw a idealized column here. Right? So an idealized column will look like this guy, right? And when it buckles, it's going to buckle like this, right? And we'll sort of calculate what P critical is. But there's a number of assumptions here, right? And I think it's important that we go through these assumptions. So the first one is that the column is straight. Right? So the column is straight. We're not going to deal with columns that are out of straight, right? So for all intents and purposes, our column is straight. Two, our load is concentric. And what that means is that the load goes through the centroid of the cross section. So I do not have any eccentricity. And three, we're going to assume that the column remains elastic prior to buckling. And if we make all of these assumptions, then P critical is dependent on three things. It's dependent on the elastic modulus of the material, the moment of inertia of the cross section, and the unbraced length. Right? So this, we want to consider this as unbraced length. Right? And you could also think about this as the length over which a half sine wave can generate, right? So this guy here is a half sine wave. And you'll see where that comes from in a second, right? But that's effectively what the assumptions that we make are. A couple things sort of maybe as an aside. So this term here, slender, right? Maybe I'll do it in red. Sort of highlight this. Right, so this guy here. So something called a slenderness ratio, right, is equal to L over R, L being the length, R being something known as the radius of gyration, which is I divided by A, right? So that is the moment of inertia of the cross-section divided by the area of the cross-section. And the reason people use slenderness ratios is it just turns out that the buckling behavior is very much related to the square root of I over A. The reason it's called a radius of gyration is if you take the square root of I over A, you get length, right, which is could be considered, some of this sort of spatial dimension, right? I is inches to the fourth, A is inches squared, right? So I divide them through and I get inches squared, and I take the square root and I just get inches, right? So it's a very sort of nice way of characterizing the specific cross section, right? And then for steel. Right, I'll do a couple here, steel, and then I have aluminum, and then we've got wood, right? And so let me, something like this. So the slenderness ratios for steel would be greater than 150. Right? For aluminum, they would be greater than about 55, and for timber or wood they would be greater than about 25, right? Now why is that? Because they all have different E's, right? Steel is the stiffest material, so I can deal with the highest slenderness ratio, right? Aluminum, not as stiff, not as strong, have to deal with lower stiffness, slenderness ratios, and the same with wood, right? Okay. So let's talk a little bit conceptually about what kind of what buckling is and what it means. And so, sort of the goal with this set of slides here. In fact, it'll just probably be this one other slide. I'm gonna generate kind of a large table here, is to give you some physical feel for what is happening and how can you conceptually think about buckling in a reasonable way, right? So we're going to have 4 columns. So I'm going to do this, I guess, in we'll do it in black. Ooh. So let's see, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3. Let me try that one more time. Let me do this. It's 5. Hopefully that works out. Let me cut across here. And then what do I have? I've got 3 from there. So something like that. All right, so we've got our table set up. And this first column here is going to be an unloaded column. And so I just realized that we've got 2 sort of definitions of columns going on. The first column I referred to is with the table, nothing else, and not the actual column that's buckling, right? So the first thing we're going to do is we're going to start with an unloaded column. Then we're going to load it with an axial force, right? So we're going to have the addition of an axial force, like that. Then we're going to have the addition of a small lateral force. I'll call that F. I'll draw these when the time comes. And then we're going to have the removal of that. Okay. So the first thing we want to do is we want to talk about what happens when, we're just going to deal with idealized columns here. So I'm going to start with, I guess, blue, right? So the idealized blue column looks like this guy. Right. Then I'm going to add a load to that column, right? So that's going to look like this. And here I'm going to say that P is less than P critical, right? So P is less than P critical, right? Then I come to this section and I'm going to bend the column like this. This is that same P, again, less than P critical. And the reason that column has bent, and I'm exaggerating it a little bit here, is that I have applied a small force F here, right? So I'm loading this column. In fact, let me do the following. I don't want to give you guys the wrong impression of what is happening here. So I'm going to apply a small force F right here. And that column then bows, right? And then when I remove the F in the last column, right, the column then comes back to where it was before. Right, and again, this is P less than P critical, right? So that column then straightens back up, right? So, just to sort of, run through this one more time, is what we're doing here is we have this unloaded column. I'm going to put some axial force on it. That axial force is going to be less than the buckling load, P critical. I'm then going to add a small lateral force. Doesn't matter what it is. You can think about just pushing with your finger on the side, blowing on it. It's a tiny force, right? if P is less than P critical, yes, my column will deform laterally. But then when I remove P critical, when I remove this small lateral force, it will come back, right? It's going to bounce back, okay? All right, so now let's look at, and I guess I'll do this in red, right? Let's look at what happens when P is equal to P critical. So this guy looks like this. My little axial force. And now we're going to do the same thing here, right? So I'm now going to apply this small force F, right? And I'm going to keep that P equal to P critical, right? And now when I remove it, something interesting happens. The column stays deformed. Okay. So it does not come back, right? So at buckling load, right, if I apply P critical, basically what I'm doing is I'm removing all of the lateral stiffness of the structure, right? One way you could think about it is I'm increasing the stress to a point that any lateral deflection, right, can be maintained because of this P delta effect. Right? So why does it remain? Why does it remain deformed? Right? It remains deformed because there is a delta here, right? And that delta times that P critical provides a moment, right? And that moment is what is keeping this deformed, right? So it's sort of like like a bow and arrow. Think about it like that, where the string of the bow and arrow is keeping the bow portion deformed, right? And so that's the situation that we're in. And now we can also look at the last case, right? Which will look something like this, right? Where I then come in and I apply a P, but now that P is actually greater than P critical, right? So you might have started to sort of intuit that, in fact, this is now an unstable situation, right? I have put it there, right? And I'm just waiting for anything, right? Something to cause this to begin to kick out. Because as soon as it starts to kick out, that P critical times that little delta is going to create a moment that's going to cause it to kick out more, right? And it's going to become unstable. Right? And so if we're going to sort of see what happens when I add that little so this guy then becomes my P. This again is P greater than P critical, right? And this is now my F, right? And this results in collapse. that results in the collapse. So when I'm at P critical, right, or above P critical, I don't have any lateral stiffness left in my column, because any deformation that is caused by a lateral force is going to be accommodated, or in fact amplified, by the secondary moment that causes, right? So my member deforms a little bit, and it gets a secondary moment that causes it to deform more, right? That's sort of this process. And the last thing I want to mention before I'll end this particular lecture, which is just, again, sort of conceptually trying to understand what buckling is that we've got to recognize that F, or this minuscule lateral force, always exists, right? So it could be initial out of straightness, initial out of straightness. It could be a small eccentric axial force. Right? We do not build our structures perfectly, so the axial force is not going to be right in the middle of the column. And it could also be due to material non-uniformity. Right? So the fact that steel may have a varying degree of elastic modulus throughout a particular cross-section, right? That could cause this eccentricity, which will result in a small lateral force, which would be the initiator of buckling, right? Now, in the case of the World Trade Center, what we see is that P was probably nowhere near P critical for those columns when the lateral support was removed. So let's say the truss system failed, the lateral force was removed, and therefore the column is just sitting there, right? It did not buckle immediately. Otherwise, those towers would have collapsed immediately, right? But they didn't. What happened was the heating of the truss, floor trusses, began to pull those columns in. And what was happening? Well, we started to effectively increase this F, right? So they were starting to pull the columns inward, and the more they bowed inward, the more that P times delta moment was able to, at first, just maintain the deformed shape, but then ultimately was able to increase the deformed shape, right? So it amplified that that deformation, and it was at that point, right, where the secondary moment, that P times delta, wasn't just maintaining the deformed shape; it was exceeding, amplifying or increasing the deformation, and then that created additional moment, which then created additional deformation, and you can see it then just became unstable, right? But again, the reason it was time dependent was because of the heating and the sagging of those floor systems, right? Okay, so that's it for today's lectures. On Friday, we will go through a bunch of examples. Well, first we'll derive the expression, which actually tends to be fairly simple, and then we'll go through a number of examples, and I'll show you some of the problems that are commonly on the FE exam. They always ask problems on buckling on the FE